Hello, this is Bruce Moore again. We're now in our fourth episode of these morning stories that we're telling, this series that's about relation space. And if you recall, relate is one of the three seeds of awareness. Relate means to join in this work. And the word relate goes on up the ladder. Relate, relative, relation, relativity. And all of those things have meaning that goes up from the seeds of awareness. The other two seeds, you recall, were in here, out there, and parts and participants. Everything is joined, and every object is joined both as a composition of parts and as a collective behavior of participants. So those seeds grow up into a model, and that's why I have my little airplane showing here. Physics uses models of the universe. Space-time is a model that says that space and time are joined in this continuum. Well, I like this little airplane because, this is a model of an airplane you could fly in, but you can't fly in this one, but it flies like the real thing, and this actually has a little motor in it and stuff. So that's the deal about this relation space model that we have here that we'll be talking about in this series, is that it's not the real universe, but it behaves like it. It has the same strange behavior of relativity that we hear in the space-time story of physics, except that in relation space, it's actually simpler and understandable. The mathematics isn't as complicated. So anyway, what we're going to be talking about today and what we'll be doing now is, instead of directly addressing the 5 things that are missing from the textbooks, and there are 5 things that are missing that are important in the relation space work, we're going to sort of sneak up on it by showing you some conceptual things that are very specific, tangible, concrete things that will take us away from contemporary story in a way that doesn't require us just to, brute force go for it. So let me show you what we have on a table down here where I can demonstrate some things. We're going to be talking about the nature of energy in this relation space story. Energy in physics is really kind of an out there thing. It's about moving material. It's about energy used to do work in that formal sense of accelerating some object. But here, energy is more of an inner flow within every atom, within us. That's the way this model works. And so we're going to do some work here that kind of heads us in that direction. So here we go. Let's take a look. So you can see here that we're going to be using origami paper for different things. And some of them will be for parents telling stories to children. This one helps to illustrate sort of like self with a stick here kind of represents a self. And then there's out there pointing directions, and there's an in here. And so you can talk about self and other joining together like that. So that's fun for parents, but so there are different things we can do with that, and we'll get to that later. But for now, we're going to be dealing with, as you can see here, squares of substance. And so that's the point here. This is going to be this substance, these squares here, each represents a resource of some sort. So the game we'll play, or the imagination that we have, is that people need parts of the resource. They need pieces, and everything is going to be dealt in squares. So they may want a small square, a large square. But this big square here represents the resource. So we'll just take this out of the picture now that we know it's origami paper. So one of the things I want to show you is that the formula for a substance like this is very familiar. Now, I've written it here exactly like Einstein's energy equation, E equals mc squared. In case you don't recognize it, that's me with a question mark. And here, if we labeled this side to be distance c, then the substance in this paper, substance in this sheet, would actually have that equation as its form. The amount of material would be some mass, each little square would have a mass, times c squared, times the area of this sheet. So mass times area. And you wonder, well, surely this doesn't have anything to do with Einstein's energy equation. But what I said earlier is that we're going to have inner counterparts in the relationship space story, inner counterparts to the outer story of physics. And there is an inner counterpart to this Einstein's energy equation, where some things that are very confusing in contemporary story become really pretty clear. So let me pop back out and talk about these origami squares for a second, and then we'll come back. So I wanted to talk a little bit more about these things, which are intended to use, this just really demonstrates a simple example of how you can use origami to help children. And I'm not nearly as talented as most people in making cute things, but here we've got something that's, we can say this represents the self that's located somewhere. This is, very specific. I kind of make it go up through the bottom. And this relates to the relation space work too, is that you've got a kind of a self here in the middle, and this self extends all out in every direction. And this actually is energy too. In relation space, everything, including an atom and a creature, a thing, is just what's the right word? It's made of energy. That energy throughout in different forms. So that's true of relation space theory, and it rings true for common sense and spiritual wisdom too. Is that there's a lot of that talk today. You'll find, and sometimes it sounds, like just too far out to be true, but that we're all made of energy and that we all join in an energetic way. But this relation space with the mathematics demonstrates a way that can happen. And with the origami, you can kind of play with children to get them the idea that they are joining with everything as they, through their senses, and joining on the inside with other things and so forth. So let's get back to the table. I wanted to show you more about these energy squares. Keep in mind that we'll be working with individual squares, but in the relation space story of energy, these squares are just flowing every second, every period of time. Might not be a second, but they just keep coming. So this square represents a resource that comes ever so often, and it's used for different things. So we're going to use a portion of this resource. Now I want to do something different with this to show you, so I'm just going to go off camera for a second, and I'm going to take a fresh sheet like this, and I'll show you what we're going to do. Now here you see I've cut that sheet right along the diagonal, and I've made myself a stick that is the distance of the side. So that length of that stick is the same as the side of the square. Now what we're going to do is we're going to rearrange this into a different kind of figure that is really prominent in relation space work, and that is a wedge. So it kind of looks like it's called a wedge, and later we'll have it turn into a butterfly. It's kind of got that shape. But see, here's the measure, and the point is that the amount of substance is the same. This is still a square of substance, 6 inches on each side. We've just rearranged it into a little different geometric shape. But the area of this shape is the square of this distance, just like the original square was. So this is a very convenient, and I'll show you why. This is a very convenient way to represent a square of substance, because it's, for one thing, it's just has one measure. This one measure instead of two. I have a hard time keeping it there. Okay, I want to show you one of the things that's really special about this. I'm going to cut this thing. Take the bottom, and I'm going to cut it like so. Let's just say right here. Okay, and what we'll find is that when we cut this bottom here, we get another square. I'll show you. So now you see I've cut this right here. So now you have another smaller wedge, and therefore another square. So in our business of selling squares of things, that's what we'll use. We will cut out either a square, or we'll cut out a portion of this that is the same amount as in this square. So let's take a look at that. So now I'm going to consider again that I've got a square of substance, and somebody wants to buy a piece of it, and what they want to buy is this much. They want to buy that much of that square. So the question comes up, well, if they buy that much, then how much do I have? What kind of square do I have left then? So here you see the piece that somebody bought, okay? And this is the size of the square that that we had as our resource. So that square would be taken out of this. Now we're going to do this. We're going to slide this up until this end meets that side of this square, and this end meets the right angle device I have. You see, I've got just a little right angle thing here. And so you could turn this anywhere, but there's only one place where it meets that end there, and it meets the right angle up there. And so what I have here is another square. You can see that it's in the shape of a wedge, but it's the same size as this square. So what I'm going to do is something kind of special here. I'm going to put that right there, like that. And of course, this is all just really approximate. But so now we've got the situation, you see, that I see what you might recognize at this point is if you look at these sides, and not this so much, you look at these sides, and we know from the Pythagorean theorem, and now here, this is what we don't want, really. The Pythagorean theorem in its contemporary form says that this squared plus that squared is equal to this squared. So that's about lengths. This is not a proof of the Pythagorean theorem. The only time you see squares like this shown in books is when they're illustrating and they're about to show you how the pieces will fit together into the original square. This isn't that. This is utilizing this resource. We've taken this much away, and we want to know what kind of square will we have left after we sell that. And what we will have left is here. It's this square with this square taken away is going to give us a square that we get from cutting this wedge. So I'm going to cut that right here, and I'll come back and put that down as a square. Here you see that I've cut it. I cut this one. So now we have this. This is the wedge folded over. So now I'm going to take that wedge apart and put it back together. Let's see if we can do it here. I've got Scotch tape. I'm going to do that offline too. So there you see it. This is the square that I'll have left after I've taken this out of here. And it deceives your eyes, but what we're doing here is we're talking about ways to add and subtract squares. And that is with the familiar Pythagorean theorem, except that we are no longer talking about, the focus is no longer on these sticks. is no longer on the sides of the triangle. The focus is on the squares. The squares constitute the resource. So there's a departure. If you look up the Pythagorean theorem in any books, then the only time you'll see this is when they're proving that the square of this is equal to the sum of the squares of these two. But nowhere do you see them using this as a resource allocation, at least nowhere that I've found, resource allocation method. Now, surely people do use it. Now, this is probably the ancient way they dealt with selling things, is by using this, because here you don't have to do any square roots or anything like that. Okay, so let me get back to the camera. One of the things that I just wanted to say is that, kind of already said it, that whereas we usually see legs of a triangle, here we don't even have those in the story. It's about this material. We sold this, and we had this, and now after we sell it, this is what we've got left. And we can say another thing: the things that I cut out, it's the same amount. This that I cut out of that square to get the remainder, this is the same amount, these two, because I cut these from this. So we have the fact that this is the same as that, and I cut this out so that these two add up to this one. So that's the same amount as that. So anyway, so now, I realize and know for sure that this video is not enough to teach you how to manipulate all these squares. That's not the point. The point is that here's one departure. The Pythagorean theorem in contemporary story is used to manipulate distances and to measure distances, whereas in this work, we use the Pythagorean theorem as a resource allocation relation. And there are some things to know about that, about when you can do that and when you can't. But the main thing is there has to be a shareable resource. So I want to give you that departure that heads us in a different direction with regard to using something that's used thoroughly in mathematics, and that's the Pythagorean theorem. But the other thing is to see that we're dealing with energy here. In the relation space, energy is what everything is made of, and it's inner energy. So that should be, for some of you, kind of exciting to think that. So in this episode, what we've done is we've held on to those seeds of awareness. And from there, we've gone a step toward understanding some of the things that are missing from mathematics. Mainly, what's missing is that interpretation, that usage of the Pythagorean theorem. Not how to prove it, but how to use it. To use it as a resource allocation. And also, this kind of points in the direction that in relation space, inner energy is allocated for different things. And if you think of yourself, you allocate energy for different purposes. And relativity is all about, or relativity in relation space is all about allocating inner energy. So we're going to stop with that one. Thank you for listening to this morning story. I hope you enjoyed it. If you do, subscribe to the channel, tell people about it, and thank you.